So hello everyone, welcome to another particular video, and in this particular video we'll start about conformers. So in our previous 13 lecture we are talking about basic stereochemistry, and from here we are doing some conformational analysis. Okay, so first of all let us understand that what is conformers. So conformers or conformational isomers are different spatial arrangement of a molecule that can be interconverted by rotation around a single bond. Like example, suppose you have this type of molecule where two chiral center is there, this type of molecule. So here is one group is here is another group is here is another group is here. Similarly, here also you can see this particular figure in the Sawhorse projection also. So what happened that this particular bond is a sp3 bond, and sp3 bond, now this sp3 bond has the tendency to rotate, and because of the rotation, what happened that these particular groups are change their position without altering their absolute configuration. Like what happened if I rotate this something like this, so and keep this particular center intact, so what happened that this will be similar, but due to the rotation, now we can say that this particular group position is distorted. However, the absolute configuration is not changed here, but the spatial arrangement or the relative arrangement with this particular group to this particular group is now changed. And this actually leads to the new isomers term, that is a conformational isomers. So it is an advanced isomerism, or we can say the advanced stereoisomerism. And this is due to the fact that sp3 bonds are capable to rotate, where if this bond is a sp2 bond, is a double bond, then it will not rotate it, but since it is a single bond having a higher p character of 7, so it has a possibility of rotate. Okay, and that's why we got this particular conformational isomers. Now I just simply remove this particular thing, and now since it is due to the rotation between the carbon carbon bond, then that's why it is called as a rotational isomers, or we can say rotamers. Okay, and also conformational isomers required about 16 to 25 kilojoule of more to interconversion. Like this particular rotation has energy barrier of very less, and that's why this type of rotation has been frequently observed in the room temperature. That's why this type of conformers are not isolable in room temperature. When we are going on low temperature analysis, so this particular bond rotation has been restricted due to the energy barrier, and that's time actually we are able to separate out this type of isomers, but in room temperature all are the similar isomers we are observed. Okay, now there is a certain difference between a conformational isomers and configurational isomers. So conformational isomers are different spatial arrangement of its atom and group that arise owing to the rotation of the part of the molecule about a single bond. This is now we are learning about the conformational analysis or conformers, whereas the configurational analysis that I discussed in the previous lectures, it suggests that configuration of a molecule is the spatial arrangement of atom and group about a rigid part of a molecule. That means that time the groups are rigid, they are not rotate through the bond. But here in conformational analysis, there is a possibility of rotate the carbon carbon double bond to form different spatial arrangement of the particular group. Okay, and obviously since the energy gap between two conformers are very less, so it will be not isolable in room temperature, whereas in configuration, since they are rigid, that's why they are isolable in room temperature. And conformational, there is nothing change actually, like their absolute configuration is same, just there is a simple carbon carbon rotation takes place, and that's why it contains same physical and chemical property. However, in enantiomers, in configurational and isomers part, like in enantiomer they are same physical and chemical property in the terms of enantiomers, but whereas in the case of diastereomer they are show different property, but both are the configurational isomers. And the another difference is interconversion of conformers involve rotation of a part around single bond that I've already discussed, whereas interconversion of configurational isomer involve bond breaking and bond making process. Just a simple example here. Suppose this type of reaction is there, and this will be the A, B, C. So this particular center is a chiral center and it contains a special rotation. Suppose I am assuming that X has the fourth priority group. So it has been a certain rotation. Now, and it's obviously since it is a anticlockwise rotation, then we can assume that it is a S conformer. Now, if we want a R conformer of this particular compound, then what happens is you have to break this particular bond and this particular group should be present here. Okay, and then only we get the opposite isomer. That is a mirror image, we'll get the opposite answer. So changing the configuration requires bond breaking and making process. However, changing the conformation will not require any kind of bond breaking or bond making process. And also the conformers having the low energy barrier, that's why it can be interconvertible in the room temperature, whereas the configurational isomer having the high energy barrier. So this is the firm difference between conformational analysis and configurational analysis. I hope this will be clear. Now, due to this particular carbon-carbon bond rotation, the groups present in there has generate some kind of strain in the particular molecule, and that's why some conformers are stable and conformers are not. So now we are talking about the type of strain in the conformational isomers. The first is the torsion strain that called as the Pischer strain. The torsion strain is occurs when atoms are separated by the three bonds which are eclipsed or staggered. And eclipse conformers lead to increased electronic repulsion causing high energy barrier. Like example here, like we are taking this particular molecule. So here I draw in the eclipse structure. I hope that in the representation of organic compound classes, we are actually know that what is eclipse, what is staggered. I have shown eclipse and staggered from there also. So here I am drawing a compound that has the eclipse structure. Now this all bonds are sp3 bond, so that means the all the bond length are equal. Okay, so what happened that this bond I have drawn here, it will be very much large, but actually it is not large. Like this bond is similar to this type of bonds. So what happened that when this type of groups are present here, if the groups are bulky enough, so what happened that there is the steric repulsion is there. Okay, in the case of eclipse, but in the case of staggered, we can see that there will be lesser steric repulsion because here the groups are not in the direct vicinity. Okay, so this type of strain is observed. This is called the torsial strain, and from torsial strain also we can talk about the steric strains. That is discussed in the next. Steric strains is called the van der Waals strain if these particular groups that present the eclipse position are big enough, then these atoms are being forced to close another, creating the repulsion between their electronic clouds, that also known as a flagpole interaction. And this is more significant in the larger molecules. Example, in butane, the Gauge conformers exhibit steric strain due to the proximity of these two methyl groups. So this particular example we will discuss in our next class, where I will show that how the energy barrier can be changed while rotating the carbon-carbon double bond and changing the conformers from eclipse to staggered to Gauge conformers. Okay. So now there is another strain is there, that is an angle strain. Now what happened that in case of sp3 carbon, we know that sp3 carbon, the between these two bond carbon H, I am taking here hydrogen only. So this particular bond have a certain angle, that is a 109.28 degree. Now what happened that in case of some kind of ring structure, such as example is a cyclopropane ring. This is a cyclopropane ring. Now here what happened, that this bond is sp3 bond, this bond is sp3, this bond is sp3, this bond is sp3. But due to this ring formation, what happened, that this particular angle is now 60 degree. That means usually the sp3 carbon, the carbon hydrogen carbon bond should present, or carbon 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 bond should have this particular angle, but here the angle has been reduced, and due to the reduction they are causing a strain. That particular strain is called angle strain. It's not only present in this particular molecule, in fact the cyclobutane, cyclopropane type of ring also, it contains this type of angle strain. And there is another strain is there, that is called ring strain. Ring strain is nothing but a mixture of the previous three strain: angle strain, torsion strain, and sometimes steric strain. And this type of ring strain has been observed in the cyclic molecule, and that's why it is named as a ring strain. Example, cyclohexane in the boat conformation experience torsion and steric strain where the chair conformer is strain free. So now you have to think about that, what is the cyclohexane boat conformer, what is the chair conformer. So I will discuss in the subsequent slides, but please remember that ring strain is a combination of all the three strains that I have discussed previously, and this type of strain only present in the cyclic ring. Acyclic ring doesn't contain any kind of ring strain or angle strain. Acyclic system does only have this particular torsion strain and steric strain, whereas the cyclic ring having this angle strain and ring strain. Okay. So after that, we are talking about the naming of conformers. Like depending upon the rotation, we can't say that it is only eclipse or staggered or gauge. Like there is some functional nomenclature is there that determine that this particular the name of this particular conformers. So here it is a simple chart that so naming of conformers. So basically, conformers are not only described in eclipse, staggered, or gauge format, because eclipse staggers are the very much precise position. Like when the both of the conformers group are present in the 0 degree, then it is called in the eclipse conformer. Whereas the groups are present in the side 60 degree apart, then it is called in the gauge conformer. Similarly, 180 degree apart rotation is called the staggered conformers or anti-conformers. But there is certain time where the particular conformers are not exactly this type of degrees of rotation has been observed. So there is a rule or we can say that there is a naming rule there to determine the conformers. That is, if the conformers are present between the -30 to +30 degree range, then it is called syn periplanar conformer. Whereas +30 or to +90 degree, if any conformers is present, then it is called synclinar. And if it is rotate in a clockwise manner, then it is called plus synclinar or plus SC. Whereas if rotate in an anti-clockwise manner and stay between this particular uh, angle group, then it will call minus SC, that minus synclinar. Similarly, -90 to -150, it is called the anticlinar, and here it is called plus part or the clockwise rotation part, it is called anticlinar. And the uh, staggered part, where the -150 to +50 degree rotation it present between this particular angle range, then it is called anti-periplanar compound. Okay, so with this we have to end this particular lecture. So in this particular lecture we have learned about a little bit of conformers, the difference between the conformational analysis and configurational isomers, and after that we are talking about some kind of strain that present in this particular conformer, such as torsion strain, steric strain, and then we are talking about the angle strain, ring strain also, and after that we are talking about the naming of the conformers. So in the next class we are talking about some acyclic conformers such as ethane, then N-propane, N-butane type of conformers, and we have studied their energy profile diagram and all. So thank you for this particular lecture. We'll meet on next lecture.